the stiffness matrix. The stiffness matrix is a Bennett matrix. That means most of the elements are zero except the diagonal elements and the next to the diagonal elements. If that's the case, we can see large MDOF. N can be very large. If I do this, then I can define. This is the definition. Delta Wi minus 1 equal to W1 Wi minus Wi minus 1 parentheses. Delta Wi equal to parentheses Wi plus 1 minus Wi. So I say, well, the distance between any spring is very small. Right? If I do that, then I can define like this. There's a definition here. Ki minus 1 delta x I minus 1, I call that equal to EA. EAA is the EA means some properties at x I minus 1. If I define that, then equation of motion for the ice mass. Now you can see that there's a delta x I minus 1 here, and there's rho. The new definition of rho is the densities, means the mass per meter. For example, this can be the kilogram per meter. Right? So m I equal to rho xi times delta x I minus 1. So we have a density. Rho is like a density. This is like a density. The mass density we call mass density. So the unit can be kilogram per meter. So rho, that's the mass density. So the unit can be kilogram per meter. That's we call the mass density. All right. EA is related to stiffness, and that's we will see it why we not define that. So if I do that, then the last equations you can see that I have moved the delta xi minus 1 to divide this the whole matrix, and then I did 1 minus delta xi minus 1, and this delta wi minus 1 and delta I minus 1. You can see that if you still remember your calculus, you can see that if delta going to very infinitive small, then this become a differential equation like that. If I do that, and the reason why I want to do this is this, because I can take the limit, then that will become continuous, and then what I want to do is this equation of motion. The last equation of motion is a partial differential equation. The density partial square W over partial T square, then parentheses is x equal to xi minus partial EA, partial W, and partial x equal to 0. And so, for very large number of degree of freedoms, I can just use this partial differential equation to represent it, rather than a huge mass matrix and huge stiffness matrix. This is just a tool. This is a mathematical tool. So to present very large system, then I say I can use this PDE just to solve it, and then I will get the frequencies. and I will get the same thing, I will get omega frequencies, I will get more shapes. And surprisingly, that many systems, such as 101, you may be able to write in terms of this kind of equations. And many engineering textbook also talk about this. That's in theory. In practice, there's no such infinite number of degree freedoms. Right? That's in practice. Because in other words, you have more degree freedom. You have more number of degrees than your number of molecules, than atoms. That's it. That's impossible physically. So, if you look at this, then that's the final equation here. Though partial square omega, partial square w divided by partial t square equal to partial x EA, partial x, partial w, partial x. So this is just a simple form to model a continuous system. All right. For example, if you have a rod, as a matter of fact, many cases, if you already take the engineering mechanics, for example, I have a rod like this, and this like that, and this is my W, all right? And I have some force here, I have some force, also force like that. Then I can write this, and this, say this is, there's a rho here on the density there, and the property of EA, this is the real EA here, that's the your property, that's represent like some kind of spring, we call continuous spring. So, if you want to solve this, then you can write this really like that. Then this partial t square partial w equal to partial x. Well, we normally write minus partial x partial EA, then partial x partial w equal to the force, which is x and t dependent. All right. So that's represent this like we call this can be a rod. And from I show you a multiple degree of freedoms and come to this PDE, just let you feel that if you have a lot of number of degree freedoms, then sometimes you can just go ahead write in terms of the PDE, then just a large size mass matrix and large size of Stiefel matrix. Okay, so that's the purpose. Okay. This is okay. Here, this just show you we can write this beam a rod in terms of this mass matrix and Stiefel matrix, or we can write in terms of the PDE. For this rod, and longitudinal vibration of the rod, you can really write in terms of this, that, and all that. A simple rod like this. If you know the EAX. But in engineering sense, if you work for Boeing company, and you likely going to write in terms of this, that, because this, most engineers have some intuitive feeling for those rather than a PDE. But they represent the same system like that. In other words, any system like this, or like 101, you can represent it in terms of a spring and mass. That's the message I try to give to you. Like this building, there's some program you can use to give you the mass matrix and stiffness matrix. In this building like this. Of course, this building, you may not be able to write in terms of like this, but in some cases you could. This is longitudinal motions. In other words, the earthquake sometimes it comes this way. It's not just only horizontal way. It's come out this way too. You may be able to write this motion in terms of this PDE. This is the PDE. This is partial differential equations. And equations. Again, the purpose I show you this is a system to be written in this large size of matrix form, or you can write in terms of a simple PDE. That's all I try to give to you. So, the PDE also can be represented by a large number of springs. All right? Understand now? Okay. The following is the beam. I'm not going to talk about this much. This is another PDE. This is not longitudinal